Hi, this video explains about the cross-validation approaches in ML models. The cross-validation is the procedure which is evaluating or validating the performance of the machine learning model by training the model on the subset of input data which is called training data, and another one is which is tested by testing data. So there is the different validation approaches available. One is validation set approach, leave p out cross validation, leave one out cross validation, k-fold cross validation, stratified k-fold cross validation, hold out cross validation. Here, the first approach, validation set approach, in this, the input data, suppose if I am having the 1000 samples of input data, the 1000 samples are splitted into training and testing, 50 percentage into training, 50 percentage into testing. That means exactly 500 samples are splitted into training, 500 samples splitted into testing. Suppose if there is triple nine, so approximately the 500 or 499, 500 or 499 will be splitted for training. Here 500 or 499, okay, 500 or 499 will be allotted for testing the data. So here exactly 50 percentage available for both phases. So due to that, there is the possibility of underfitting. Underfitting means the uh, model unable to learn patterns from all, most of the data, most of the data samples. So because there is the possibility of underfitting. Okay, so next one is leave p out cross validation. Here p number of data points will be used for testing purpose, then remaining n minus p number of samples will be allotted for training the model. It will be repeated for all combinations. So finally the error will be averaged. Here suppose p is 3, p is 3. In the output, input data 1000 samples, 3 samples will be allotted for testing, 997 samples will be allotted for training. Then next time again another 3 samples will be allotted, then another 997 samples will be allotted for training samples. So here different 3 samples, next iteration another 3 samples. So here you will get one error and here you will get one error. So then finally you will be averaging the errors. You will be averaging the errors of all iterations. This is very exhaustive model and computationally which is infeasible. It will take time. It reduces the bias when comparing with the validation set approach, because which is using all the training samples in the different different iterations. Then leave one out cross validation. So here only one data point will be using for testing for each iteration, and remaining 999 will be allotted for training samples. Okay, so this will be done for all the training samples. So 1000 times, so 1000 times you have to iterate this. Finally the error will be averaged. So this process minimize the bias, but it will take much execution time, because it will be using 1000 times each single sample as a testing sample at each time. So it will take more time for execution. It leads to high variation, because here the model is perfectly learning the patterns from training data. Okay, there is the possibility of high variation between testing and training accuracy. Then another one approach is K-fold cross validation. This is the most popular cross validation. Most of the professionals are using this cross validation. Here, uh, due to we are getting the more data from the real-time environment, the machine learning model never gets sufficient patterns from the input data, right? So to train the model. So it leads to underfitting due to loss of important patterns, which increases the bias of the model. Bias means the uh, training accuracy and testing accuracy both are more. Okay. uh, for that we can apply the k-fold cross validation, which is dividing the input data set into k number of equal size of group. That means suppose I am having the 1000 samples as input. If my k value is 5, then it will divide that 1000 samples into 200, 200, like this. So 200 samples here, 200 here, 200. So 1000 is divided by 5. Okay, so 5 groups will be divided. Then here each group I will explain with example. Here the data is 1000 samples. Then here we are making the 80 percentage of data. Okay, 80 percentage of data training, 20 percentage of data for testing. So in the 80 percentage of data we are having the 800 samples. These 800 samples will be divided into 5 groups. You look at that: fold 1, fold 2, fold 3, fold 4, fold 5. So this 800 is divided into here 160 samples, here 160 samples, here 160, 160, 160. So 5 sixteens are 80, 800. Okay, so here uh, 800 is divided into 5 folds. Then this fold and the first iteration, in the first iteration, okay, first split. Okay, so this will be using for validating the model. These four folds are using for training the model. Okay, after training this model will be tested by, this model is tested by fold 1, fold 1. Okay, likewise now after uh, after that the parameters will be updated second time. Okay, second iteration, this second fold is assumed as a testing data. The remaining fold 1, fold 3, fold 4, fold 5, these are using for training the model, right? This will be tested by fold 2, right? So this is testing, this is training. So training by fold 1, 3, 4, 5, tested by 2. Then third split, fold 1, 2, 4, 5, these are using for training the model. The fold 3 is used for testing the model. Like that, here the split 4 is using for testing the model. 1, 2, 3, 5 are using to train the model, right? So finally we will get 1, 2, 3, 4 for training the model, 5 is using for testing the model. So here all the samples are trained to learn the patterns, and all the samples are using at least one time for validating the model. Okay, so here the parameters are updated to improve the model. Finally our model is ready. Finally our model is ready. So this model is called trained model. This model is called trained model. This trained model now will be tested by this testing data, 20% of testing data. So here you will get the training accuracy, here you will get the testing accuracy. So due to using fold of samples for each time you are using the fold of samples, your execution time is decreasing, and also which is improving the model by reducing the bias and variance. So this is the procedure of KFold cross validation. So which is providing more accuracy due to learning the patterns from every sample. Observation means sample, training sample. So that is the advantage of K-fold cross validation. Next one is stratified cross K-fold cross validation. Stratified means here in data set there is the balanced and imbalanced data set, data set. So K-fold cross validation does not perform better for an imbalanced data set. Imbalanced data set means suppose if we have 1000 samples, in that 1000 samples there is the possibility of two classes, class 0, class 1. If class is 0 is having only 200 samples, class 1 is having 800 samples. Okay, in this 200 samples, during the training, suppose the in this 0 class 0, for the training if we take only 50 samples, then testing will take 150 samples. So here you see 50 samples here training, but here suppose I am taking the class 1 samples. Class 1 samples may be 700. You see class 1 samples are 700, but class 0 samples are only 50. So this is called imbalanced data set. Okay, so in this case K-fold cross validation will not suitable. For that what we are applying, we are applying the stratified K-fold cross validation. In this, each fold each fold will contain each fold, that means we are splitting the data into folds, am I right? So each fold contains approximately same number of samples for each class, same number of samples for each class, that is called strata. That means suppose if I am having the 200 samples uh, of zeros class, then here 40 samples for each fold will be allotted. Okay, 40 samples for each fold will be allotted. Okay, from the zeroth class, right? So same number of samples will be allotted for each fold. That is the purpose of stratified K-fold cross validation. It reduces the both variance and bias. Then holdout method, so which is a simple method which is used to remove a subset of training data and use it for predicting the data by training, and testing data will be used rest of the data. It results high variance due to smaller size of training data, because which is again taking less number of training samples, so there is the possibility of high variance, and it needs to run once, so spend lower computational cost. Only once it will be run, so that's why it will take only less time. Then there is the evaluation matrix to evaluate the model. So first one is confusion matrix. The confusion matrix is used to measure the performance of model based on the summary of number of correct and incorrect predictions. So here actual output is given, actual label. Okay, label output, there is the positive samples and negative samples. That means 0 1 0 1 like this. Okay, so 0 means positive, right? 1 means negative in the cancer data set. So like that actual labels are taken here, then our model will predict, machine learning model will predict the output. So that samples, negative samples are taken here, positive samples are taken here. So here when the given data is 0 in table, okay, in the table given data is 0, right, the table given label is 0 for first sample, and our model also predicted for the first sample as 0. Okay, so you look at that, this is predicted output and actual output. Okay, actual output is also 0, predicted output is 0. That means this is positive, sorry, negative, this is also negative. Okay, so 0 predicted also negative, our actual output which is given in the table data set also negative. That means both are negative, means both actual and predicted outputs are negative, means that is called true negative. True negative. Suppose my second sample is here, you look at that 1. Okay, second sample my predicted output is 1, then my actual output is also 1. Okay, actual output is taken from the table, okay, from the second sample. So this is calculated by our machine learning model. So both are positive. Okay, both are positive. So when both are positive, okay, both actual output is also positive, predicted output by our model also positive, that means true positive. True positive. Then suppose if the first sample, in the first sample my model is, my model first sample I am taking, my model is predicted as, okay, predicted as 1, but in the table, okay, actual output in the table is, you look at that, first sample is 0. Okay, you see my predicted output is 1, but my actual output is 0. So actually which is negative but predicted as positive. So this is wrongly predicted as positive. Wrongly predicted as positive. So wrong means false, so wrongly predicted as positive. So false positive. False positive, you look at that, my actual output is negative, but my model is predicted as positive, so which is called false positive. Likewise, when second sample, you look at that, my model is predicted output is predicted output is here 0, that means negative, but my actual output is, okay, actual output is, sorry, negative means 1. Okay, negative means 1, but my actual output is positive. So here it is positive, right, sorry, this is negative. Okay, 1 minute. Right, so my model is wrongly predicted as, wrongly predicted as wrongly predicted as negative. Okay, wrongly predicted as negative, right, negative means 1. Here my actual output is positive. Okay, so if this is negative, this is positive. Okay, so which is called false negative, which is called false negative. Look at that, my actual output is positive. Okay, my actual output is positive, right, but my model is predicted as negative, so which is called false negative. So this one is wrong, I will explain one more time. You look at here, my table output is 0 first sample, second sample is 1. My um, my model is predicting the output is positive. Okay, but my actual output of the first sample is here 0. Okay, so if both are 0, that means which is true negative, which is true negative. Okay, if both are positive, if both are positive, then which is true positive. And next one, my model is predicting as 0, right? 0, but my actual output is 1. So this is actual output is 1, but predicting as 0. This means which is positive, but wrongly predicted as negative. Wrongly predicted as negative. So this is look sorry this is positive, this is negative, so this is called false negative. False negative, you could look at that. Actually output is positive but predicted as negative, false negative. Then if my actual output is 0, if my actual output is 0 but wrongly predicted as 1, wrongly predicted as 1, so this is positive, this is negative. Okay, negative, so wrongly predicted as positive, so my actual output is 0, 0 means negative. Okay, but wrongly predicted as 1, 1 means positive, so false positive, right? So from this we can calculate, this is what I have given here. uh, we can calculate sensitivity. Sensitivity formula is true positives divided by true positive plus false negative. That means ability of detecting true positives from number of actual positives. So this is also actually positive but falsely detected as negative. Okay, then specificity, percentage of actual negatives correctly predicted as negative. Okay, so here the true negatives divided by true negatives divided by false positive, actually which is negative, falsely detected as positive, right? Then accuracy is total number of samples are correctly predicted. That means true positives plus true negative divided by all the samples, all the samples. Okay, correctly identified, positive as positive plus negative as negative, then divided by correctly identified positives, correctly identified negatives. This one falsely identified as positives, this one is falsely identified as negatives. So this is the accuracy, but it is not suited for imbalanced classes, imbalanced data set. Precision is the correctness here, which is defines the total number of samples are correctly identified as a positive from the actual positive samples. Okay, actual positive samples. From here you look at that, true positive divided by true positive plus false positive, this is actually negative samples falsely identified as a positive samples. Then recall is the another measure which is used to predict the positive classes from actual positive classes. You look at that, true positive divided by positive as detected also positive, here positive samples but detected as negative samples, false negative, right? Then there is the F1 score, which is also used to measure the classification, which is averaging the evaluation metric. The F1 score is 2 times of precision and recall divided by precision plus recall. Okay, so already we got precision recall, from that we can calculate the F1 score. The range is from 0 to 1. If F1 score is close to the 1, your model is performing well. If a model is close to the 0, then performance is not good. That is the thing. Here, uh, the true positive rate and false positive rate is given. True positive rate means true positive rate plus true positive rate divided by true positive rate plus false positive rate. If it is true positive rate close to 1, the model is better, right? True negative rate, which is if it is close to 1, model is better. False positive rate, if it is close to 0, the model is better. False negative rate also, if it is close to 0, the model is better. And the misclassification rate is calculated by the false positive plus false negative divided by total number of samples. The total number of samples can be written as true positive plus true negative plus false positive plus false negative. Okay, then there is another one metric, area under the curve, So this is area under the curve. You look at this. This is called ROC curve, receiver operator characteristics curve. Okay. So when you are adjusting false positive rate and true positive rate, right? So false positive rate and true positive rate, if both are close to 1, you look at that, both are close to 1. Both are close to 1 means then your model is performing well. The area under this ROC curve is called area under curve. So if your area under curve is more, if this area is more, then our model is better. If area is very less, if area is, suppose my curve is like this, then my area is very less, so this is representing our model is not performing well. So there is different machine learning algorithms, supervised, unsupervised, and reinforcement. This is for the reference. So with this, I will conclude the session. Thank you.